agree with me now? Please? All right. Give you peace of mind. Good. I want you to understand about this, because that will be, we will need that later on. So we need that later on. Okay. So, this basically, let's come back to this one. All right. So now is transient. One is a transient response. One is forced response. So we have when you xk, you sub this xk equal to yk equal to cxk plus duk. Cxk, we have xk and put a c there, and we have a c there, and then this is my transient response in the measurement. So we have a transient response and forced response, and transient response become zero if x0 equal to 0. If you don't have initial conditions, then x0 equal to 0. So the transient response x0, the transient response will be gone if if A is a stable matrix. That means all eigenvalues of A are less than 1. And when K is sufficiently large, then CAK AK becomes just 0. For a large K, then CAK x0 becomes 0. That's very, so the transient response will be gone for stable system when times go on. That's why I want to prove to you that why for a stable system the eigenvalue of A less than 1, so the transient response become not very important when K become sufficiently large. And we'll tell you the next chart is become observer model, because that will lead to us to talk about observer model. That's become an important observer for your controller design. Then I'll look at the basic combination for this. The observer equation is fk plus 1 equal to ask plus buk. Then I add a term called gyk, subtract another term called gyk, and that means my equations. Sk plus 1 equal to ask plus buk, that doesn't change, because I add one term and subtract one term, and I will tell you why I want to do that later. Then I sub, this is arbitrary. Then this is yk, I sub yk equal to cxk plus duk. So now if I substitute yk equal to cxk plus duk, only sub 1. This yk equal to cxk plus duk, and then I put I put with the front, put together with the state matrix term, a state vector term, then I get A plus GC, SK plus B plus D, the GD, parenthesis UK minus GYK. Then if we define A bar equal to A plus GC, B bar equal to B plus GD minus G, and V, K equal to U, K, and we stack the U and Y together, and we can rewrite these equations. That's what we call observer equation. This observer equation, you need this observer equation for any state feedback. We'll talk about state feedback very soon. For the state, you don't measure. For example, that if you have a measurement only accelerations, then you don't have velocities. You don't have displacement. Now, how can I estimate my velocity? How can I estimate my displacement? Of course, you can integrate that. But if you don't know initial conditions, you cannot integrate that. For that case, you need observer equations. Now, observer equation is the equation for you to estimate the state you don't measure. That's the purpose for observer equations. All right. Now, because G is arbitrary, so A plus GC, I can choose my C. I can choose my C such that the eigenvalue A bar will be my desired eigenvalue. Now, because Z is arbitrary, right? Z is arbitrary. We may choose a G such that the eigenvalues of A bar equal to A plus GC. We can choose such that the eigenvalue of A bar equal to A plus GC are we can choose the G such that the eigenvalue of A bar equal to A plus GC as desired. All right. Now, so what kind of eigenvalue I wanted to have for A bar? So the point is, what eigenvalues? What eigenvalue of A bar? What eigenvalue of A bar? Do we how can I eigenvalue A bar being 1? Well, you can think about it. You want to be as stable as possible, for example. Right? For example, the A bar is